Now we're going to get into the second type of rate law, which is called the integrated rate law. Remember that the differential rate law is about relating the rate of the reaction as a function of concentration of the reactant. However, in the integrated rate law, this is relating the concentration of reactant as a function of time. So you'll see that all the equations would have concentration on one side and then some function of time on the other side. So you might wonder why this would be necessary since we already have that one equation from the differential rate law. And the reason is because there's some practical issues that is better addressed using this form of an equation. So for example, if you take a medicine or a drug and you want to know how long it takes before you have to take it again, that's a question of concentration of the medicine as a function of time. And so that's better answered using the integrated rate law. If you drink alcohol and you want to know how long it takes before the level of the alcohol is low enough that you can drive, that's also a question of time and reactant concentration. Much better addressed using the integrated rate law than the differential rate law. There's some specific applications that we'll talk about having to do with radioactive isotopes, and a lot of times we wanted to answer similar questions like, if we have a particular radioactive isotope, how long will it take for that isotope to decay such that we don't have to worry anymore about the amount of radiation that is generating? So a lot of these things are answerable using the integrated rate law. Now, the reason why it's called the integrated rate law is because you can get the equation by doing what's called integration, right? Which is an operation in calculus. In this class, you're not required to have taken calculus, so the equations would just be given to you. However, I would quickly derive one of them just to show you the steps of how we get this equation. So I'm going to derive it for the zeroth order, and then you see for the first and for the second order, it'll be the same steps. It's just that the integration will yield different types of equation. Okay, so now we go back to that part of the notes that shows you the derivation of the zeroth order. You start with the expression for the zeroth order rate law. So you remember that the rate law, generally speaking, always has this form: rate equals K times concentration of the reactant, let's call it A in this case, to the power of some order. So if you're dealing with a zeroth order, that means your M is equal to 0. So then your equation just looks like this: rate equals K times 1, since anything to the 0 power is 1. Now the rate itself, of course, is just expressed as negative delta A over delta T. Remember, that's how we define rate with respect to the reactants. But now we're talking about instantaneous rate as opposed to average rate. So we're going to use the symbol D for a really tiny change in time as we're looking at the reaction. So then we start with this expression: negative dA dt equals to K. Those of you who have taken calculus are pretty familiar with this expression on the left, because that's usually something you would write when you take a derivative of a function. Then we're going to do some step that called the separation of variables. We have two different variables, concentration and time. We're going to take one to one side and take the other one to the other side. It's sort of like doing your algebra cross multiplication type. Once we have the two variables on separated side, we're going to do what's called an integration, and this is the symbol for that operation. And we're going to do this from time 0 to time t. So we're going to integrate from 0 to t for both sides. And then an integration is a mathematical operation for those of you who are not familiar with it, and it gives you certain functions as an output. So in this case, when I integrate a function like this, dA from 0 to t, what I get is just a, and it's going to be what we call evaluated from 0 to t, meaning that there's going to be two answers to it. The one answer is a at time t, and then the other one is a at time 0. It's the initial point to the final point. We're going to subtract final minus initial. So that's what I wrote on this side, is the result of the integration from 0 to t. And then on the other side, the dt itself is integrated from 0 to t, so it gives us just t minus 0 as the final minus initial, multiply by the negative k. And then so we work out everything, we isolate this a t variable on one side and put everybody else on the other side. This is the final equation that we get. And so this equation is your zeroth order integrated rate law. Now, if that derivation that I just did made absolutely no sense to you because you've not taken calculus before, don't worry about it. Then what you need to do is just memorize this equation that I've bought for you, okay? Now, before we go further to talk about the first order and the second order equation, I want to describe the variables that I'm listing here. So A with the subscript T refers to the concentration of A at time T. Okay, so it's the concentration after the reaction has progressed a certain amount of time. So whatever is left of the reactant at that point, that's what A sub T represents. K, of course, is our rate constant. T itself is time. And then A naught is the concentration of A initially, okay? Or sometimes we just call it A at time zero. Doesn't have to be time zero, it's just anything earlier than the A of T. So let's say the A of T is 10 minutes, the A naught could be at 2 minutes. So it just represents an earlier time point during the reaction. So remember that this one that I'm showing you is the zeroth order. If you want the first order, you would pretty much do the same step that I just showed you with respect to the integration and the separation of variables. And in the end, you're going to get an equation. The equation would look like that. Usually the way we would write it is we would put the concentration at time t on one side and then everybody else on the other side. So it would look something like this. So if you want to memorize this, this is the one you're going to need to use. Okay, and just to be clear, in this class, you have to memorize all the equations. You're going to be given the constant if you need them, like the gas constant, Avogadro's number, but equations have to be memorized. So in this case, that's our first order integrated rate law. Now, this function you should have seen in your prior math class. This is called the natural log, and you have a button on your calculator that will allow you to make that calculation. But we'll go through briefly this idea of natural logs and exponents in our first laboratory meeting, so everybody's at least reminded of what these things represent, okay? The other equation you need to remember is the second order equation, which is shown here. So for that one, after all the separation of variables, then what you're going to get in the end is this equation right here. Let me write it down for you. It would look like this is second order integrated rate law. It's going to be 1 over A equals to KT plus 1 over A. Okay, and again, the meaning of those variables is the same. A lot of times we don't actually write the t, so you notice that here I have a sub t, but here I just remove that t. I didn't put it in just because there's an understanding that when you write it as just A, that means it's the concentration of the reactant at some later time, and then A naught is the concentration at an initial time or earlier time. All right, now that we learned the three equations for the integrated rate law, we can apply it to different situations that we are going to encounter in chemical reactions. So here's an example. It says the rate constant for the decomposition of cyclobutane at 500 degrees is 9.2 times 10 to the minus 3 per second. How long will it take for 80% of this sample of cyclobutane to decompose? Okay, so whenever you're trying to do calculations with the integrated rate law, the most important thing is really to figure out which integrated rate law to use. Remember that you have three of these: zeroth order, first order, and second order. So you have to figure out which order are we dealing with. And remember that we had discussed this idea earlier where the unit of the rate constant can tell you what reaction order you're dealing with. So what we need to do then is look at the question and see what the rate constant unit is. The unit of the rate constant is per second. Per second is inverse time. If you look at that table, anything with inverse time would be a first order reaction overall. So that tells us that we have to use the first order integrated rate law equation. So first order equation looks something like this. Your goal here is to solve for time. How do I know that it's looking for time? It says how long. So I'm going to arrange the equation so that I only have time on one side and then I have a bunch of everything else on the other side. If I do that, it should look something like this. I have ln of A over A naught divided by negative K. Notice that the A over A naught is in parentheses, so it's the natural log of that ratio. Now the question becomes, what numbers do I put in for A and A naught? The question doesn't really give you the value of A or A naught. Okay, all it says is how long will it take for 80% of the cyclobutane to decompose. Well, we know that at the beginning there is A naught concentration of reactant. And after that amount of time, 80% of it has decomposed. Here's where you have to remember the meaning of that variable A. A here represents the concentration at time t. So it's the concentration of the reactant that's left at that time. So if 80% of it has decomposed, that means that the A at time t must only be 20% of A naught. Okay, now what I need to do is substitute those to the equation. So 20% A naught over A naught, the A naughts cancel away, so it's just the ln, natural log of 20%, which is going to be a negative number. It's given right here, and then divided by the rate constant, which is this other negative number, because it's negative K. The unit is per second. It's at the bottom in the denominator, so then inverse second, 1 over inverse second becomes second, and then if you do the division, you get 175. It'll take 175 seconds before 80% of the cyclobutane is consumed.